Okay, so 10.3 part 1, we're going to talk about what polar coordinates are. And so you guys are used to Cartesian coordinates, sometimes referred to as rectangular coordinates, where you have the xy coordinate plane. Um, and a coordinate really, right, is just an address, or it's like directions to get somewhere in the plane. So if I have, I don't like that line. All right, so if this is my rectangular coordinate plane, my Cartesian coordinate plane, and I'm having a party over here, and I want to give you directions to that party. I could say, okay, the directions are -3, 2. And that just tells you that starting at the origin, you're going to go -3 units to the left, and then you're going to go you're going to go up +2 units, and you're at the party. All right, well, there's another way I could give you directions to that party from the origin, and we could think of it in terms of r theta. So I could tell you as well, starting from the positive x-axis, go rotate theta radians or theta degrees, stop, and then go out a radius of length r in that direction. And that would also get you to that point, right? And that's exactly what polar coordinates are. So it's just another way of describing a location in a coordinate plane, but you're doing so in terms of an angle of rotation and a radius instead of an x direction followed by a y direction. Okay, so a couple definitions that I want to start with. This is called the polar coordinate system. It's useful for many things, namely describing things like spirals and also conic sections, we'll see, are very well described by polar coordinates, whereas they're a little bit more complicated to describe using Cartesian coordinates. And you guys have seen that before, like a circle is described in Cartesian form like this if it's centered at the origin. If it's not centered at the origin, it's more complex. And you're used to it at this point, which may make you feel like, well, that's not that gross looking, but they're much easier to describe using polar coordinates. All right. So the way we deal with polar coordinates is we start with the pole, which is basically our origin, and then we draw a line, and usually we'll just orient it almost the exact same way as the Cartesian plane. So we'll draw the polar axis, usually just off to the right. So this is like our starting point, right? So this would be my polar axis, and this would be my pole. Okay. So if P is any other point in the plane, R is the distance from the pole to P, so from O to P, and then theta is the angle, and we're going to be measuring in radians, between the polar axis and the line OP. And we describe this point P in polar coordinates as r comma theta. So this labeled diagram is a good diagram to have that kind of labels everything. So remember that that is called the pole. All right, so the ordered pair r comma theta are called polar coordinates of P. And we use the convention that the angle is positive if we rotate counterclockwise, and the angle is negative if we rotate clockwise. So this is all stuff, I mean, the normal way of measuring angles. All right, if r equals 0, then the ordered pair 0 theta will represent the pole for any value of theta. So one thing that's interesting about polar coordinates is that every point is actually going to have infinitely many ordered pairs that can correspond to it, right? So if I have, like, let's say that's the point 1 pi over 4. Well, I would also have a corresponding point that could be found by rotating again all the way around. So adding 2 pi to that, I could say that's also the point 1. 2 pi would be what? 8 pi over 4, so 9 pi over 4. And then I could just continue to add 2 pi, and I would get another polar coordinate that corresponds to it. All right. Here's a weird one. If r is negative, so if you have a negative radius, the way that we're going to graph negative r theta is you would basically go rotate to theta. You would imagine if r was positive, then you would graph positive r theta here. And for r to be negative, you go in the opposite direction, the same magnitude of r. So this is negative r theta. So it's on the opposite side of the pole. So this is going to give you the same point as r theta plus pi, right? Because this would be the rotation of theta plus pi. Pepper, can you drink more loudly while I'm teaching? Okay, is this making sense so far? Any questions? So if r is positive, r theta will lie in the same quadrant as the angle of rotation. If r is negative, it's going to lie in the quadrant on the opposite side of the pole. And as I just said, negative r theta represents the same point as r comma theta plus pi. All right, so we're going to jump to, I think, some examples. Oh, well, I should have erased this. All right, let's do this. Can I just erase these? Close your eyes for a second. Sorry. Okay, now we're good. All right, just because I want to practice graphing these with you. Hey, Henry and Jill, you're being too loud. All right. So let's start with 1 5 pi over 4. And all we really need to do is get it roughly in the right place. I don't need you to break out the protractor, measure out a perfect 5 pi over 4. But let's start with just our pole and our polar axis going off to the right. And then 5 pi over 4, so we know the quadrants are pi over 2, pi, and 3 pi over 2. Is 5 pi over 4 larger than 3 pi over 2 or smaller than 3 pi over 2? Is it greater than 3 pi over 2 or less than 3 pi over 2? Right, because 3 pi over 2 would be 6 pi over 4, right? So smaller, so that's all I want you to do is get it roughly in the right quadrant. So 3 pi over 2 is the quadrantal angle that goes straight down. So 5 pi over 4 is going to be like here. And then we want to go out, let's call this, we want to go out a distance of 1. I'll make that slightly smaller. And this will only matter for when we graph the rest of them. All right. And then I'll usually want to indicate my angle of measurement with a little arc showing the direction that I'm rotating. So this is the point 1 5 pi over 4. Good. All right, what about the point 2 3 pi? Okay, there's my pole and my polar axis. 3 pi is going to be 1 pi, 2 pi, 3 pi. And then I want my radius to be 2, so I want to make it roughly twice the size of my radius that was 1. So I'll say 1, 2. And this is the point 2, 3 pi. All right, so then let's do 2 negative 2 pi over 3. All right, here's my pole, here's my polar axis. So negative 2 pi over 3, I want to rotate in the opposite direction. So I want to rotate clockwise. Where is negative 2 pi over 3? Let's see. Is it more? Let's compare it to pi over, let's compare 2 pi over 3 to pi over 2. So pi over 2, 2 pi over 3 is 4 pi over 6. Pi over 2 is 3 pi over 6. So it's more than that. So it's going to be past the first quadrant rotating clockwise, but it's definitely less than pi, right? Okay, so we're going to go past this quadrant, which would be negative pi over 2, but we're not going to go all the way to the other side, which would be negative pi. Let me back this out a little bit. Okay. So we want to go to right about somewhere in here. And I'll go out a distance of 2, so 1, 2, and again, I'm just trying to roughly compare these to units of my 1 unit radius. And so that's the point. 2 comma negative 2 pi over 3. All right, last one. So negative 3 pi over 4. So let's start with our pole and our polar axis. Negative, okay, so 3 pi over 4, we want to rotate. 3 pi over 4 is more than pi over 2, but less than pi. So it's going to be in that second quadrant. So I want to rotate over to here somewhere. Now, if it were a positive radius of 3, I would want to go out 1, 2, 3 radii, and I would put my point here, right? But it's a negative radius, so let me make this a dashed line. So we're going to go out in the opposite direction of that angle. So this is my angle, 3 pi over 4. So I rotate to that, and then I go out the opposite direction. 1, 2, 3, and I place my point. So that's the point represented by negative 3 pi over 4. Okay. Questions? All right, let's keep going. So this is something I already mentioned, but in Cartesian coordinates, every point has only one representation. But in polar coordinates, every point actually has infinitely many representations because we can do different things, right? So here's 4 representations of the same point. The most kind of straightforward one is 1 5 pi over 4. So that's like your most concise. You're just rotating to that angle, and then you're going out a radius of 1. But we have many others. We could do rotate there in the negative direction, in which case it would be 1 negative 3 pi over 4. I could go around twice and then stop there, right? Or I could go there once and then come back around. So I could add 2 pi essentially to it. And then that would be 1 13 pi over 4. Or I can make my radius negative, so just rotate to pi over 4, but then go to negative 1, and that's going to be at the same location. And again, we could get infinitely many more of these because we could always just continue to add more rotations of 2 pi and get a new angle. All right, so now we're going to talk about how do we convert between Cartesian coordinates and polar coordinates, or vice versa, and we're going to do that using a right triangle. So any Cartesian coordinate and its corresponding polar coordinate will form just this right triangle relationship where x and y are the legs of the triangle, r is the hypotenuse, theta is the radius of rotate, or the angle of rotation, I should say. And so we can just use basic right triangle trig to define the relationship between cosine theta and sine theta. And I'm sorry, between x and y and r and theta. So cosine theta would be adjacent over hypotenuse, so x over r. Just multiply both sides by r. X equals r times cosine theta. Sine theta is y over r. Opposite over hypotenuse. Multiply by r. Y equals r sine theta. And so this is an easy way of converting from polar to Cartesian. If you know the polar coordinates, then the corresponding Cartesian coordinates will just be r cosine theta, comma r sine theta. And so what I want to point out is this is actually a set of parametric equations because r is a constant and we could treat theta as a variable. So it's very easy to convert from polar form to parametric. All right, well, what if we want to go the other way? Sorry, so if you want to go from in the opposite direction, so from Cartesian to polar, it's a little more work, but it's definitely doable. The relationship between x, y, and r is just Pythagorean. So r squared equals x squared plus y squared. And then the relationship between x, y, and theta is just tangent. So tangent theta equals y over x. So theta technically is arctan of y over x, right? Or inverse tangent of y over x. All right, so we're going to kind of practice translating between those. All right, so say I have the point 2 comma pi over 3, and I want to convert, that's in polar coordinates, I want to convert to Cartesian coordinates. So I know that r equals 2 and theta equals pi over 3. And so Cartesian coordinates are xy coordinates. I'm going to use that conversion that we had a couple slides ago, which is x equals r cosine theta and y equals r sine theta. So my x coordinate is 2 times cosine pi over 3, and my y coordinate is 2 times sine pi over 3. So pi over 3, if I convert that to degrees, is 60, right? So this is we're talking about a 30, 60, 90 triangle situation here. So say that this is 30, this is 60. Goes 1, 2, rad 3. All right, so we're looking at the 60 when we evaluate these. So cosine of 60 is going to be adjacent over hypotenuse, so 1/2, right? So my x coordinate is 2 times 1/2, which is just 1. My y coordinate, 2 times sine of pi over 3, so sine of pi over 3 is going to be opposite over hypotenuse, so root 3 over 2. So that's 2 times root 3 over 2, which is just root 3. So my y coordinate is root 3. There we go. The Cartesian form of the polar coordinate 2 pi over 3 is 1 rad 3. Let's go the other way. So now if I'm given Cartesian coordinates, let's find the corresponding polar coordinates. So the point 1, negative 1. All right, so here I have x equals 1, y equals negative 1. We have that relationship. So really, right, what we have, you can almost think of this in the coordinate plane if you wish. So 1, -1 is going to be down here. That's -1, +1 here. And if I draw in my hypotenuse, that's my radius, right? So, all right, so r squared equals 1 squared plus -1 squared. So r squared is 2. So r is √2. And then we need theta. And so we know tangent of theta is opposite over adjacent, -1 over 1, which is -1. And so theta is just going to be arctan of -1. All right. So when is tangent negative? At what angle would you get a tangent that would give you -1? So this is actually a special triangle. This is a 45, 45, 90 triangle, right? Because it's technically isosceles. So theta is 45 degrees, but we're rotating clockwise here. So it's actually going to be -45 degrees, right? And in radians, that's pi over 4. So theta equals -pi over 4. So you have to take a little care when you're doing these conversions and recognize where you are in the coordinate plane. So r equals, so it's r theta. We found out that r is rad2. Theta is -pi over 4. And there are other options, of course, because we're talking polar coordinates here. So you could technically give me other answers to this question that would be correct, right? You can tell me, actually, I rotated this way. And so what's 2 pi minus pi over 4? That's 7 pi over 4. So an equivalent correct answer would be rad2 7 pi over 4. I mean, I don't know why you would want to go out of your way to do the extra work, but it would be correct. Any questions so far? Okay. So now we know how to plot points. Now we want to get to imagining curves. So we write the graph of a polar equation in the format r equals f of theta. And it consists of all points that have at least one polar representation, r theta, whose coordinates satisfy the equation. And so we're doing the equivalent of, right, when you're in like pre-algebra, you start by just graphing coordinates. And so I would give a pre-algebra class like, okay, here are a bunch of coordinates, graph those out, right? And be like, okay. And then we go, oh, those all seem to fall on a line that we could connect. Is there another way we could express that relationship? And then you kind of level up to algebra and you realize, oh, okay, well, we can kind of generalize what's going on here and just say y equals x. And then you learn to graph functions, right? And so that's what we're doing here. We started off graphing just points, and now we're going to look at when r is a function of theta, sort of more general relationships. Oh man, hold on. Okay. Spoilers. I forgot to take the stupid answer animations out of this set of slides. All right, so this is example 4. And if we just think about in Cartesian form, when I give you like y equals a constant, what sort of a graph do you get? So I'm just talking about in Cartesian coordinates. What sort of a graph do I get if I just set y equal to a constant? Horizontal, but yes, a line, right? X equals a constant is vertical, so just have a line. All right, I placed it in there. What about when we're talking polar functions and I just let the radius be a constant? And so it's understood, right? When I graph in Cartesian, I let y be a constant. We're letting x take on every other value, right? And y is just being a constant. So same thing here. If I just let r be a constant, it's understood that I'm letting theta cycle through every possible value. So if r is 2 and theta is a constant, and theta is, let's say, 0, I would get that point, right? If r is 2 and theta is pi over 2, I would get this point. If r is 2 and theta is, let's say, pi over 4, we're going to get this point. So if we let r be a constant, we let theta cycle through all its possible values, we're just going to get a circle. And that's a circle, remember, just of radius 2. What if you let theta equal a constant? What if I go, okay, let's say theta equals pi over 4. Well, in the Cartesian plane, if we let x be a constant, okay, let's say x equals 2, I get a similar thing to when y equals 2. I just get a line, right? What's your intuition for if we let theta equal a constant and we let r cycle through all its possible values? Who was that? Tommy? Very close. Very close. Half right. Exactly half right. If I let theta equal pi over 4, I would rotate to pi over 4. And r is allowed to take on all values possible, which if r is positive, will just give you this ray. But remember, r can be negative, in which case the graph is going to go in the opposite direction, right? You get a line. That's exactly right. Yeah, so when theta is a constant, you get a line. When r is a constant, you get a circle. Okay. So, and we'll kind of just focus on what's going on with r as theta increases. So when theta is 0, plugging it into that function, I have 1.5 to the 0. My radius is 1, right? And so I want to think of this in terms of the origin is my pulse. So if I rotate to angle 0, so that's just the positive x-axis here, right? My radius should be 1. So I'll say that this is a radius of 1 here. So I'm going to go out in that direction, positive 1. All right, well, what's another easy angle? Rotating halfway into that quadrant would be pi over 4, right? So if my angle is pi over 4, then I have 1.5 to the pi over 4 power. So let's see what that is approximately. I'm just going to put that function in there, 1.5 to the x. I'm going to go to my table. All right, so all I have to do is plug in pi over 4 to my table here. All right, so we get 1.375. So my radius should be slightly larger than what it was before. I said 1.375. So I need to go out. I'm going to go to my angle of pi over 4, which is halfway in, and I need to go out slightly further than I went out before, right? So that's going to be like, let's say something like that. All right, well, what about at pi over 2? .89, so even further. So at angle pi over 2, my function needs to be even bigger. So you can kind of get an idea about what's going on, right? So my curve is starting like this, and then as we rotate through the angle, the radius gets larger, right? All right, so next, halfway through the next quadrant would be 3 pi over 4. That was 1.89. All right, but remember what exponential growth does. It may start off kind of slow, but it very quickly is going to get really large. So my radius is now about 2.6. So halfway through, even bigger radius. All right, and so that's generally the idea, right? Is as we increase our angle, our radius is just going to kind of continue to get bigger and bigger more and more quickly. And it's going to quickly kind of spiral out of whatever our frame of view is because it's exponential. So I'll show you what the curve actually looks like. We started here at 0, and so we were graphing it coming out of the through positive values of theta. Here, they started with negative values of theta, which is fine, and they went from -3 to 3, so their curve is starting over here. But yeah, it's just an ever enlarging spiral, right? That's going to quickly, no matter what frame you use, it's going to spiral out of that window pretty quickly because it's exponentially growing. All right, give me a second. We're going to do one more, I think, and then actually I'll just show. All right. So this one is, it was meant to do the same thing. I'm giving you kind of the Cartesian version of this graph, and I want you to sketch it as a polar curve. So this is actually what it's going to look like as a polar curve here. And let's just talk about why it would look that way, and I'll kind of trace it out as we go. So remember, on this graph, the x-axis is theta and the y-axis is r. So let's just start here. At the origin, I have angle 0 and I have radius 0. So that puts me right at the pole in my polar coordinates, right? 0, 0. Same starting point. All right. So as we increase our angle to pi over 2, our radius constantly increases to 1, right? So as I rotate through this first quadrant between 0 and pi over 2, I need my radius to constantly increase through that rotation until finally at pi over 2 my radius is at 1. And you can see that's what's going on. So as we rotate, my radius is increasing, right? And I'll kind of draw lines to show that. As I rotate through, that radius gets longer and longer at a constant rate until once we've rotated 2 pi over 2, my radius is 1. Boom. So that's an angle of pi over 2, and that's a radius of 1. So we've dealt with sort of the first section of that kind of piecewise function. All right. So let's talk about what's going on in the second quadrant. So between pi over 2 and pi over 4. So here, my radius is just a constant of 1. So as my angle increases between pi over 2 and pi, my radius rather, is just a constant of 1. Remember that we said that when your radius is a constant, what you get is a circle, right? So in that quadrant, we're basically just going to have a quarter circle. So that's a quarter circle with a radius of 1. All right. Now about halfway through the next quadrant, what happens? Well, my radius starts at 1 and it decreases to 0. But that's only at halfway through the next quadrant. So that's to that angle, I need my radius to start at 1, which would be right here. And it's as I rotate through that quadrant, we're going to decrease our radius down to 0, right? So it starts here all the way at 1, and then as we rotate through, that radius just continues to rapidly decrease down to 0. All right, but once we're halfway through that quadrant, right? So between 5 pi over 4 and 3 pi over 2, basically, our radius goes negative. So this is where it gets kind of confusing. So remember what when a radius is negative, that means we go to the opposite side of the pole. So even though we're rotating through this quadrant down here, since our radius is negative, it's always going to be graphed on the opposite side of the pole, which is going to be in quadrant 1. And so it's decreasing to -1. So it's actually going to be graphing over here until I get a radius of -1. So once I'm at 3 pi over 2, which is this angle down here, right, I would graph a radius of -1, which is actually going to be up there. So that's where that little loop inside our loop in the first quadrant comes from. And now we're rotating through the last quadrant here, and our radius continues to be negative, but it increases towards 0, right? So our radius continues to be negative. It starts at -1 up here, and as I rotate through that fourth quadrant, it increases towards 0. And that's where that second loop in quadrant 2 comes from. Just one more quick explanation. So if I have r equals 1 plus sine theta, that's just the sine curve shifted up 1. So this one's kind of nice and maybe a little easier to visualize because there are no negative values that I have to worry about of r that are going to put me on the opposite side of my pole as I'm rotating. But I'm just rotating from 0 to 2 pi. So that's just one full rotation. So at 0, I'm going to have radius 1. So that starts me at this point at the top. Oh, I'm sorry. No, that's not correct. That starts me at this point here, right? And so when I go to pi over 2, you can see what's happening is that my radius values are increasing from 1 to 2. So as I rotate through that first quadrant from 0 to pi over 2, my radius is going to increase up here to 2. And then from pi over 2 to pi, so that second quadrant, my radius is going to decrease back to 1. So, boom, back to basically this distance is 1. And I've rotated in a full angle of pi there, right? Then from the third quadrant, pi to 3 pi over 2, my radius is decreasing from 1 to 0. So that gives you that little, as I rotate through there, I want my radius to get closer and closer to the pole until at 3 pi over 2, I'm at the pole. And then that last piece comes from rotating in the fourth quadrant, 3 pi over 2 to 2 pi. My radius should increase from 0 to 1. So from 0 back to 1, meeting us back at our starting point. And that's a shape called a cardioid. Real quick, we can graph polar functions in our calculators. So we're going to change it from function mode to polar. Quit out to the main menu. Now when you go to y equals, there you go. Instead of y's, you have r's. So let's graph that last curve we just did. If I do 1 plus sine, and now when you try and click x, boom, it's a theta. Let's go to window. And so just like when you graph parametric equations, it's going to make you give some different parameters for polar. So you have to tell what values you want for theta. Let's go just one rotation. So that's 0 to 2 pi. And again, it needs a theta step because it's going to compute these as a bunch of points and connect them. So you want to keep it relatively small so that you don't get a jagged version of connect the dots. You get a nice smooth curve. So around 0.1 is fine. Here, the biggest our radius ever got was 2. So in the XY window, I don't really need to see out from -10 to 10. Let's just go from -3 to 3 for both X and Y. All right, and then I'll hit graph. And there's my cardioid. Again, because our screens are rectangular, it gets a little distorted. So if you do the zoom 5, it gives you kind of a better version of that. And if you ever need to know how it's being traced out and you want to slow down the graph, you can always just make the t step or the theta step in this case really small, and you'll be able to see what it's doing a little bit better. So there's our cardioid. Can mess around with some other stuff if we do like a constant. Let's say I do r equals 1.5. That should be a circle with radius 1.5, right? Make concentric circles. So there you go. That's how you graph polar functions using your calculator. What I want you to do as you work on the problem set is try and have an intuition for the graph, right? Try and think out or maybe sketch out what you think it's roughly going to look like, and then you can graph in your calculator. And that'll just start to help you develop a better intuition for how polar curves will look based on their equations. Because it can be hard, especially when you're so used to dealing with Cartesian coordinates your whole life and you've kind of trained yourself to think that way.